Hello and welcome to another tutorial on VSEPR theory. This is the second of 5 tutorials which is going through how to do VSEPR, and this one in particular is about how you do it with incomplete octets. This is relevant to any student who's covering the IB chemistry curriculum or if you're doing any post-16 course which requires knowledge of VSEPR. I'm going to talk through first of all how it links into the curriculum, and then I'm going to go through some examples. So the link to the IB curriculum is similar to what I've said in earlier videos. So the application is deduction of Lewis electron dot structures of molecules and ions, showing all valence electrons for up to 4 electron pairs in each atom. I'm not going to go through ions in this particular video, that will be in a future video, so we'll put that on hold. Other things as well is the use of VSEPR theory to predict the electron domain geometry and the molecular geometry of a species with 2, 3 and 4 electron domains, and the prediction of bond angles and geometry. So the objectives and the links to the IB curriculum are exactly the same as a previous video, but now we're just dealing with the idea of an incomplete octet, which is a different part of the specification, which I think is under the knowledge and understanding. So the acronym we're going to use is exactly the same as what we used before, which is Dirty Vinny Bit My Dust Early Morning. Now, as a breakdown, the D in dirty refers to diagram, the V in Vinny refers to valence electrons, the B in bit refers to bonds, the M in my is multiple bonds, the D in dust is divide for electron pairs, and the E in M is electron and molecular geometry. Now if you watch my previous videos you know exactly how this works, but I'm just now going to apply it to more unusual molecules. So let's start with BeH2. Now beryllium is Be, it's a metal and hydrogen is a non-metal. So you'd normally expect these to have ionic character, but actually beryllium can do some covalent style bonding which can confuse. So let's go for this molecule assuming that it does covalent bonding. So we're going to start with D for dirty, which is the diagram. Now I would assume by looking at this that my beryllium is in the center. So I'm just going to draw what the diagram will look like. So just getting this out. So here's my beryllium, and I'm just going to draw my hydrogens either side. Okay, so that's my diagram. And now I have to think of my valence electrons. Now my beryllium is my central atom. Beryllium's in group 2, as we know, because you can see that it is from over here. So as a result, I start with the number 2, because I've got 2 valence electrons. My next step is to think of the number of bonds. Now it's made 2 bonds to each hydrogen, so I have to add 2, 1 from each. So 2 plus 2 equals 4. Now in this situation, in terms of the M for multiple bonds, there are no multiple bonds, so I'm going to consider that to be 0, I'm going to ignore it. Moving on to the next D is divide for electron pairs. So I've got 4 electrons from over here. I divide that by 2, and that gives me 2 electron pairs. Okay? So my next step, which is to draw the electron geometry, well, I start with beryllium, and because I've only got 2 electron pairs, they have to form this linear structure like this. So I've got a hydrogen over here and a hydrogen over there. So in terms of my electron geometry, it has to be linear. And then in terms of molecular geometry, I've got 2 electron pairs and both of them are dedicated to bonding. There's no lone pairs, which means that the molecular geometry has to be same as the electron geometry, which is linear. Okay? And then finally, let's deal with bond angles. Well, we know it's linear, there's no lone pairs interfering with anything, so it has to be 180 degrees. Okay, and we're done. So that's an example of an incomplete octet. Notice around the beryllium, it only has 4 electrons in its outer shell, but that's, in this rare case, that's okay. Let's try another one. Let's have a look at BF3. So let's start with D for diagram. So I start with boron, which is in BF3, and it must have, in one way or another, 3 fluorines attached to it. Now I'm going to go through the process as usual to see whether that is an accurate representation of what I've got. So I start with V for Vinny, which is valence electrons. Boron is in group 3, as you can see. So as a result, I have to write 3. I now have to consider the number of bonds. Well, there are 3 bonds from the 3 fluorines attached to it. So it's 3 plus 3, which equals 6 electrons. All right. Next step is to consider multiple bonds. There are no multiple bonds here. I can ignore that step. Move on to divide for electron pairs. So I've got 6 electrons. I divide by 2, and that gives me 3 electron pairs. All right. Next step is to find the electron geometry. Well, I've got 3 electron pairs, so I know that my structure is eventually going to be trigonal planar. Something there, and something there. Now I have to work out my molecular geometry. Now before I do that, I'm just going to write my electron geometry as being trigonal planar, which is by trig planar. And my bond angle will be somewhere close to 120. Whether it's smaller than that, we'll find out later. Now, for the molecular geometry, I need to see what's attached to these 3 electron domains. I have 3 fluorines, as you can see. So it must be a fluorine there, a fluorine there, and a fluorine there. So my molecular geometry is also trigonal planar, and the bond angle remains 120. Notice here that we only have 6 electrons in the outer shell of boron, and in this case that's okay. Okay, so that's fine. We're done. Okay, we'll try one more, and this is SnCl2, which is tin chloride. Again, I start with D for dirty, which is my diagram. Now again, I'm just going to assume that I've got Sn in the middle and chlorine either side. Right? Now let's do my valence electrons. Tin, or Sn, is in group 4, so it's got 4 electrons in its outer shell. Next step is my bonds. I've got 1, 2 bonds, so it's plus 2. So I have 6 electrons to play with. Ooh, 6 electrons to play with. My next step now is to think of multiple bonds. There are no multiple bonds from my prediction here from before, so I'm going to ignore that and consider it 0. Next step is to divide for electron pairs. So it's 6 divided by 2, which equals 3 electron pairs. Now I need to do the E for early and the M for morning. Now for early, it's electron geometry. So if I've got 3 electron pairs, it must be Sn here, bond there, and or pairs of electrons in those 3 areas. So I know that my electron geometry from this is trigonal planar. As a result, my bond angle must be somewhere around 120 degrees. I'll refine that later. Now I'm now going to finish off with the M for morning, which is molecular geometry. Now I have 2 chlorines, so I'm going to put 1 there and 1 there. But we're left with this space. This is a pair of electrons, but they're not involved in bonding, so it has to be a lone pair. So I'm just going to get my rubber, rub it out, and replace that with a lone pair. So my molecular geometry is no longer trigonal planar because there's nothing here, it's simply bent. And to finish off my bond angle, because of this lone pair taking up more space, there's greater repulsion between the lone pairs with the bonding pairs compared to bonding pairs alone. That means that this will be slightly smaller than 120 because my chlorines are pushed together a little bit more. So it will be a little bit less than 120. And that's your VSEPR analysis for incomplete octets. Okay. I hope it's been useful. Good luck with the rest of it.